Alright, so for this video we're going to go over chapter 10. However, before we go into chapter 10, I will have to introduce scatter plots from chapter 2, section 4. Alright, so definition of a scatter plot. Scatter plot is a graph of ordered pairs of data values that is used to determine if a relationship exists between the two variables. So we're going to have two separate variables, independent variable and a dependent variable, and we're going to see if there's a relationship between the two that connects them. So we're going to see if there's a correlation between the two. An alternate way of stating this definition is a scatter plot is a graph of ordered pairs, so x and y, of numbers consisting of the independent variable x and the dependent variable y. So anytime we're graphing a scatter plot, the independent variable will fall on the x-axis and the dependent variable will fall on the y-axis. Alright, so correlation refers to the existence of a relationship between two variables. So we're going to have two separate variables and we're going to see if there's a relationship between the two. And what do I mean by a relationship? Let me just throw this out there. For example, carbohydrates and fat. Okay, so obviously carbohydrates has a lot of calories, which has a lot of fatty acids, right? So is there a correlation between carbohydrates and fats? So in this case, which one's the independent, which one's the dependent case? Well, which one's the independent, which one's the dependent variable? Well, let's look at the definitions here. When data is collected on two numerical or quantitative variables, in order to determine if there is a correlation, the researcher will designate one of the variables as the independent variable and the other as the dependent variable. So the independent variable, so the explanatory variable, if you remember from chapter 1, the variable that explains, that's the way I would put it, it explains what's happening, is the variable that can be controlled or manipulated. The dependent variable or response, so the one that a response occurs to it, so there's a response to it, so it changes, so it depends on the independent variable, is the variable that cannot be controlled or manipulated. So in the case that I just gave, or the example that I just gave, so the carbohydrates, right? The carbohydrates, I can control how much I eat. So I can control it. It is the independent variable. It is trying to explain if I am adding calories and more fat to my food, right? The dependent variable would be the fat, because I can't control the fat that I eat. I can't control the fatty acids that I eat. However, I can control the carbohydrates, and if adding carbohydrates adds the fats to my food, or adding it lowers, right? Or adding it, or removing carbohydrates, whatever the case is. The fact is, I can control my carbohydrate intake, so therefore it is the independent variable that's trying to explain the dependent variable, which is my fatty acids, which is the food, right? That I'm eating. So again, independent variable, right? Independent variable is the variable that I can control, that I can manipulate, while the dependent variable depends on the independent variable and either changes to the positive or changes to the negative. So, a positive linear relationship exists when the points fall approximately in an ascending straight line and both x and y values increase at the same time. So if you look at graph A, positive linear relationship. So again, these plots here that you see in front of you, these are what we call a scatter plot. So it's just a bunch of scattered points. So if you look at graph A, a positive relationship, a linear relationship, again, linear just means it is a line. So to have a linear relationship, you must have a line. So as you can tell, A looks like a line. So it is a positive linear relationship because both x and y are positive. So both x and y are increasing, ascending order, so going up. While a negative linear relationship exists when the positive fall approximately in a descending straight line from left to right. So again, as you can tell, y and x are decreasing towards the right, from left to right. So let's think of a line, right? A line is positive going up to the right, and the line is negative going left to right. You do not have for C, a non-linear relationship exists when the points fall in a curved line. So anything but a line would be non-linear. So if you look at a scatter plot and it does not look like a line, so it looks like a C shape, U shape, V shape, any type of shape that's not a line, that is a non-linear relationship. And for D, there is no relationship, just a bunch of scattered plots all over the place. There is no relationship. There's no curve, there's no line, there's nothing, just scattered plots. It's random, there is no correlation there. Alright, relationship between variables. It is reasonable to assume that a relationship exists between the number of hours a student spends studying and the student's grade point average of GPA. A student can control the number of hours that he or she spends studying. So in that case, the studying would be my independent, while my dependent would be the GPA. So this is how I would word it. Depending on the depending on the number of hours I spend studying, my GPA will be affected. So if I study less, chances are, from just logic, my GPA will be lower. If I study more, my GPA might be higher, but that all depends. So a study was made, and here are the statistics that we received. We have in hours spent studying, 22 hours, 22 hours, 21 hours, 20 hours, 18 hours, and the GPAs that connect with those amount of studying. So what we're going to do is we're going to plot all of these numbers into a scatter plot and see what kind of correlation we have. So after plotting those points, we notice that if we look at the scatter plot, we notice that there is a positive linear correlation between the time of studying and the increased GPA. So even though some numbers, as you can tell from the scatter plot, some are lower than others, some are higher than others. For example, if you look at 10 hours, you'll see somewhere near 10 hours, between the 10 and the 15. So if you look over here, you'll see that, sorry, let me just fix my pen. If you look over here, you'll see that there's a dot lower than this one. If you look here, you'll see kind of, going up. You'll see here another one where there's at the same points, but two lower GPAs. Even though they studied the same amount of time, there is a lower GPA. You'll look here, there's a big chunk of lower GPA, even though they studied the same amount of time, and whatnot. However, we don't look at single points. What we like to look at is the overall pattern. So kind of like the average of all, And we're going to be talking about this in chapter 10 about, the best fit line, the regression line, and all that stuff. We're going to be talking about that. But for now, if you look at this, if you look at the way the points are going, and you kind of visualize a line that really takes the average of these points, you'll see that it is positively correlated with obviously a positive linear correlation between GPA and the time of study. Alright, so now we're going to jump into chapter 10, correlation and regression. So I'm going to combine sections 1 and 2 together. So you're not going to feel like I moved to another section. It's just going to be 2 sections together. Alright, so correlation coefficient. Statisticians use a measure called the correlation coefficient to determine the strength of the linear relationship between two variables. So our correlation coefficient is going to be a number, and that number is going to tell us how strong the correlation is. I mean, as you can see from the other graphs that we showed, there's a positive linear correlation, and then there could be another positive linear correlation. I mean, if you look at, let's say, this, you'll see that looks like a positive linear correlation, but then if you look at this one, you'll see that it's kind of closer to each other. These points are close, so these points here are closer than these points here. So which one's better? Which one is better? Which one is more correlated? Which one has a stronger correlation? That's where the correlation coefficient comes about, and there's a formula to calculate it, and we'll see how that is done. Population and linear correlation coefficients. So the population correlation coefficient denoted by the Greek letter rho. So it looks like a P. just kind of a fatter head in a sense, is a correlation computed by using all possible pairs of data values x, y taken from a population. So in some cases we know every data point, so we use every single data point. In some cases we may not know every data point, but we use as much as we know, as many data points as possible. The linear correlation coefficient computed from the sample data measures the strength and direction of a linear relationship between two quantitative variables. The symbol for the sample correlation coefficient is R. So that number R, or rho, will tell us the direction in which the correlation is going, positive or negative, right? And how strong it is. So how close to a perfect line is our correlation. So the linear correlation coefficient ranges between the values of -1 and 1. So when I say that, I mean R cannot be greater than 1 and R cannot be less than -1, keeping in mind that the closer you are to -1, so let's say -0.9, the stronger negative linear correlation it is, and the closer you are to 1, the stronger positive linear correlation you have. And the closer you get to 0 in the positive sense, so think of, let's say this is 0.5, right? You're starting to have a weaker and a weaker positive correlation. Somewhere here, you may not even say it's a weak positive correlation. You might say it's a no correlation, especially at 0. There is absolutely no correlation. And then once you pass 0, once you cross 0, now you're in the negative zone. There is still no correlation with -0.1. However, the closer you get, you're starting to get a weak, let's say 0.35. Now you have a weak negative linear correlation. You pass 0.5 and you get here, now you're starting to have a stronger negative linear correlation, or a strong, or moderate. I would say more moderate at 0.6 and 0.7. I would say moderate. Strong would be 0.85, 0.9, 0.80. All right, so just like I said, the stronger positive is the closer it is to 1, right? So when the linear correlation coefficient has a value close to 1, it indicates a strong positive relationship between the variables. In other words, as the values of the explanatory variable increase, so do the variables of the values of the response variable. So again, as x increases, y increases as well. And same goes for the strong negative relationship. So when we say strong negative relationship, again, x and y are both decreasing. As the explanatory decreases, as the explanatory increases, the response variable decreases, right? Because x is always increasing, and the reason for that is because we're using x values to test our statistic, right? So we are moving to the right of x at all times, right? So x is positive, so as it's going that way, y is negative, right? So y is going down while x is always getting greater. Even when it's in the positive direction, x is positive, y is positive. However, here y is negative and x is in the positive, right? A weak relationship, so obviously the closer it gets to 0 on both ends, the weaker the relationship becomes, like I just stated before. When correlated, values of the explanatory variable and response variable are perfectly linear with a positive slope, and value of the linear correlation coefficient R is equal to 1. So if R ever equals 1, then you have a perfect line. You just have a straight, perfect line, and every point touches that line. Perfectly correlated variables do not occur in nature. Some variations is expected. As variations occur, the scatter plot of the correlated variable can appear to have an approximately linear relationship. When this variation increases and the band that captures the scatter plot becomes wider, the value of R begins to approach 0, which is pretty much common sense. When you have a perfect relationship, which again rarely happens, to have something perfectly occur linearly. However, some points might occur, like outliers might occur every now and then, so it kind of ruins the scatter plot. So if you look at this scatter plot here, if I were to draw a line, I mean, it goes through all of those points, but it kind of skips this point, this point, this point, that point, that point, which lowers my R. So the correlation becomes a little weaker than to be strong. But this would still be a strong correlation. I mean, I would assume that this R would be somewhere around 0.92 or 91. However, it does get lower and lower as these dots on the outside increase, the more we have. When correlated values of the explanatory variable, response variable are perfectly linear with a negative slope, then the linear correlation R is -1. So again, if you have a perfect line, but it's going down towards the right, from left to right, then you have a negative correlation. And if it's perfect, which again rarely occurs, then it would be -1. And the same case occurs if you have scattered plots going negative, just like in the positive case. You have a lot of dots on the outside, so it's going to get closer to 0. So you're going to go from let's say -1 to -6, -0.6 to -0.5 to -0.4. So you're going to go down to the right towards 0. Unlike the positive, when we're going down towards the left. This scatter plot shows the relationship between the length of the femur in centimeters and the height in centimeters for a sample of adults. Now, just a crucial note here. Anytime you're doing any form of scatter plot, the measurements have to be the same. The measurements have to be the same. So if you're using centimeters in Y, use centimeters in X. You want them to be the same. So there's no misinterpretation anywhere. Although there's quite a bit of variations, again, let me just say something else. You do not want a misleading graph. Again, recall that from chapter 2. We do not want misleading graphs, and something like that might occur. So keep that in mind if it ever occurs, that you use the same measurements. Although there is quite a bit of variation in this data set, the majority of points appear to have somewhat a positive linear relationship. The linear correlation coefficient for this data set is R equal to 0.363. So if you look at this graph, you might look at it and say there is no linear relationship, right? You might say it's just, scattered all over the place. However, later on when we start doing a best fit line and we kind of try to picture this, kind of ignoring the outliers in a sense with your mind, because those two dots affect, they affect the correlation drastically. However, in some cases there's only a few, so does it really affect it as much? So what I mean is, if I had quite a few, they drastically affect it. Like, they really do affect it. But if I only have like 2 or 1 or 3, right, compared to how many I have here, I kind of can ignore the outlier in a sense and kind of look at the main graph here and indicate that it is positive. If you really look at the dots, they're kind of facing up, going towards, positive Y and positive X. So I can say it's closer to positive, definitely scattered, so it cannot be a strong correlation. So you could assume it's between 0.2, 0.3, right? And then the real number is actually 0.36. Another correlation here, and if you could see here, you'll see that, it's quite a lot of points, and you'll see there's a lot of, connected kind of lines going up, but we don't want to look at that. We kind of want to avoid looking at that. What we want to look at is always the line that kind of crosses all of these points in the middle, kind of giving you the average of what you're looking at, right? So that's what you really want to look at. So you kind of want to look at, you know, these dots here and these dots here, in a sense, cancel each other out. These dots here, the fact that they are on the same line kind of cancel each other out. They don't cancel each other out, but you kind of want to think about that because we're talking about averages. So you kind of look at the big picture here, and if you think about it, you kind of have a symmetric, right? You kind of have a symmetric image there. So you kind of have a 50% correlation because of that symmetry that kind of exists. And again, we'll be doing formulas to find the exact value, but I'm just giving you the eye test, how you can kind of measure the R. You know, you kind of look at it, you kind of see that it's kind of symmetric, so you know it's kind of going to average each other out. You definitely can see that it's going up. You can see that it's positive correlated, so you can make an argument that it's 0.5 in a sense. Another correlation, you'll see that this is a scatter plot that shows a relationship between horsepower and fuel, and you'll see that it is a negative correlation. However, it is non-linear because, as you can tell, it is creating a curve. So it is a non-linear relationship. So this relationship would be non-linear. It is negative, however. Let me just make a point as well. Negative does not mean bad. Okay, it does not mean bad. Think of negative, for example, if I practice running, right? So the amount of practice I do for running, and I want to finish a marathon in less than an hour, for example. The more I practice, the faster I finish the marathon. However, the more I practice, that's the independent variable because that's what I can manipulate, right? I can practice, let's say, 30 hours a week. And then I finish the marathon in let's say a 10-mile marathon or whatever in 1 hour. So say I practice 30 hours, right? And I finish the race in 1 hour. Then I, bumped it up to 40 hours. I was able to finish in 50 minutes. And then I bumped it up to 50 hours. I was able to finish in 45 minutes. And you can see that my X is increasing, my independent variable is increasing, while my dependent, right, my race time depends on how much I practice, is decreasing. So there's a negative relationship between the two. But does that mean negative is bad? I mean, I want to finish the race faster, right? I want to finish the race faster, but there's a negative relationship. So is that a bad thing or a good thing? I mean, this is actually considerably a good thing, right? So negative and positive do not mean if there's a negative relationship or a negative correlation that it means anything bad. Horsepower and fuel efficiency, I want to spend less fuel and more horsepower. So I want there to be a negative correlation between the two. So keep that in mind anytime you're doing these problems. So correlations, again, here's just some images about correlations. As you can see, 0.5 is kind of a scattered straight line, positive, right? Kind of a scattered, when I say a scattered straight line, I mean it's scattered and it looks like it's about to create a straight line. Unlike B, it's 0.90, you can see that it's a line. You could definitely see it's a line. You could definitely see it's positive. However, you can see that it's not perfectly straight, so you can see it's closer to 1. Unlike C, which is exactly 1. And if you look at all three graphs on top, all three graphs on the bottom, they're the exact same graphs. The only difference is they're negative, so they reflect on y equals x on the diagonal line. So they kind of reflect off this line here, as you can see. They reflect off that line. So, formula for the linear correlation coefficient R. So here's the formula, where n is the number of data pairs. So n is the sample size. It is a large formula to do by hand. Luckily, there is a way to do this using the calculator. I will definitely show how it's done on the calculator in our live sessions. However, at this moment, I will teach you guys how to do it by hand. It is very good to know how to do these by hand so you can check your answers in case you forget the inputs for the calculator. So compute the linear correlation coefficient for the data points. So we have car X, so 63, 29, 20.8, 19, and revenue Y. So these are the revenues. So again, depending on the car, the price and the revenue differs. So car X would be my independent, and my revenue obviously depends on my car, so it's my Y. So XY just means X times Y. X squared means every X I will square. So I'm gonna do 63 squared for the first box, 29 squared for the second box. So this is just 63 times 7, 29 times 3.9. This is 63 squared. This is 7 squared, and so on. After calculation, so it's really helpful to actually draw a box and a table to just help you organize your data points. Once we have our xy's, once we have our x squares, and once we have our y squares, we can then add, so the sum of x would be adding all of these up, the sum of y would be adding all of these up, the sum of xy would be adding all of these up. This is not supposed to be 3,969. I just noticed that. So let me just quickly see what 63 squared is. Oh, 63 squared is 3,969. Why did that seem such a big number? Oh, because the next number is 29. Never mind. This is actually correct. I thought I made a typo. So again, summation just means add these up, add these up, add these up. Now you have every number you need. Now you have every number you need. All you have to do is plug them into the formula. So again, here's where you place the sum of xy. N is the number of values that we had. We only had 6 data points. The sum of xy was 682.77. The sum of x was 153.8, and so on. You just input your numbers in your calculator, and we get a correlation number of 0.982. The linear correlation coefficient suggests a strong positive linear relationship between the number of cars a rental agency has and its annual revenue. That is, the more cars a rental agency has, the more annual revenue the number will have. I mean, the more cars you have on your lot, the more likely that you will sell, right? I mean, 29 car lot can sell a maximum of 29, while 63 car lot can sell more than 29 cars. So common sense that the correlation would be very strong. All right, we'll try this example. I mean, you could always pause the video here, try it out on your own, try to do it, the number of absences, and the final grade. So we're looking at the correlation between students and their number of absences and their final grade. So assuming that the more they're absent, the lower their grade is. And we'll see the correlation here. So here are the numbers. If you did this example, here are the numbers. Again, you just add up the x's, add up the y's, multiply each y with each x. Not each y and each x, each respective y with its respective x. So each pair, multiply them together, square every x, square every y, add them up, plug them into the formula, and we get a negative 0.944. Does it make sense to be a negative correlation? Of course it does. The value of R suggests a strong negative linear relationship between a student's final grade and the number of absences a student has. So in logic, the more absences a student has, the lower his or her grade will be. Of course it has to be a negative correlation because the more absences a student has, the lower their grade will be. So hypothesis testing with scatter plots. So to make this decision, you use a hypothesis testing procedure. The traditional method is similar to the one used in the previous chapter. So of course you're going to state the hypothesis, you will find the critical values, compute the test value, make the decision, summarize the results. Assumptions for testing the significance of the linear correlation coefficient. The data are quantitative and are obtained from a simple random sample. So again, they are random and they are quantitative, meaning numerical. A scatter plot shows that the data are approximately linear related, so they should be linearly related. So you cannot be using a test on a non-linear graph. There are no outliers in the data, so you have to make sure that there are no outliers in the data. And the variables x and y must come from normally distributed populations. So we have to assume normality for the variables of x and y. No, the null hypothesis will be rho equals 0. The null hypothesis means that there is no correlation between x and y variable in the population, and the alternate will be rho does not equal 0. The alternative hypothesis means that there is a significance correlation between the variables in the population. This is crucial to understand what we are doing. What we are testing for, is there a correlation or no correlation? So the null hypothesis, the original belief, is that there is no correlation, while the alternate is there is a correlation between the two, because you are testing to see if there is a correlation. So, and when we say there is a significant correlation, we do not necessarily know if it's positive or negative yet. We just know that there is a correlation between the two if we reject the null. So if we reject the null, we'd say that there is a correlation. If we fail to reject the null, then we say that, chances are there is no correlation. When the null hypothesis is rejected at a specific value, again, that would be the significance level, it means that there is a significance difference between the value of r and 0. When the null hypothesis is not rejected, it means that the value of r is not significantly different from 0 and is probably due to chance. So just like I said. Formula for the t-test for the correlation coefficient: t equals r square root of n minus 2 divided by 1 minus r squared. Again, r would be our correlation coefficient, n would be our sample size, with degrees of freedom equal to n minus 2, where n is the number of ordered pairs x, y. Very crucial. We're used to using the t-test for n minus 1. However, the degrees of freedom will be, in this case, n minus 2. Only for correlation problems that it is n minus 2. I know that is a little annoying. However, knowing that it's a correlation problem against non-correlation problem, we definitely know that when to use the degrees of freedom of n minus 1 and n minus 2. So, test the significance value, or the significance of the correlation coefficient found in example 1 if we did use alpha equals 0.05 and r equals 0.982. Now, I don't have to bring back example 1 because I found what r is. I mean, we found r, and r is 0.982, so I wrote r here. We're going to test the significance of the correlation between with the significance level 0.05. So, again, alternate would be rho equals 0. The null is rho equals 0, and the alternate would be rho does not equal 0. Since alpha equals 0.05, and there are 6 sample size of 6, then 6 minus 2 is 4. So the degrees of freedom is 4. The critical values obtained from table F are plus or minus 2.776, right? So as shown here, we have negative 2.776, 2.776. Again, we are drawing and assuming normality. All right, at a significant level 0.05, we have to test to find our t value. So we plug in our r. 6 minus 2, square root of 6 minus 2 divided by 1 minus 0.982 squared, we get 10.398. 10.398 is a crazy number, much greater than 2.776. So we make a decision to reject the null since the test value falls in the critical region. So there is a significant relationship between the number of cars a rental agency owns its annual income and its annual income. So if you look closely, again, 10 is a much bigger number than 2. So it's clearly in the critical region. So we reject the null hypothesis. Another example, but this time we're going to be using table I. Again, to find table I, it would be under important formulas on Canvas. Test the significance at alpha equals 0.01 of the correlation coefficient R equals 0.442. Using table I though. So, solution, since the sample size is 10, there are n minus 2, so 10 minus 2 equals 8 degrees of freedom. So you're going to, for any correlation problem, degrees of freedom will be n minus 2. And we are using table F or table I, which is a T table and table I. Table I is just a refined version of table F. The critical values obtained from table I at alpha equals 0.01 and 8 degrees of freedom are plus or minus 0.765. Since 0.442 is less than 0.765, again 0.442, that was the value of R that we had been given to us in the original problem, the decision is not to reject the null. So anytime we are using table I, what we do is compare directly to the critical value that we have, which is what we have been doing even in the previous problem. So we fail to reject the null since 0.442 is less than 0.765. Remember, we rejected the null because 10 was greater than 2.776. However, in this case, 0.442 is less than 0.765, so we do not reject the null. So I kind of, copied this one even though it should look like a normal distribution. However, the reason why this one does not look like a normal distribution is because what we're looking at is the correlation, right? The correlation line is between -1 and 1. Okay? Our correlation was 0.442. But with a significant level of 1% of the data that we have with 8 degrees of freedom, to reject, I should have gotten a correlation of 0.766 or more, right? So let me explain this one more time. My correlation is between -1 and 1, right? Between -1 and 1, as shown above. For this to be a significant relationship, getting a 0.442 was not strong enough at a significant level of 1% of the data that I have. To be strong enough, I should have fallen at the greater than 0.765. So therefore, I failed to reject the null hypothesis. So there is not enough evidence to say that there is a significant linear relationship between the two. So there is no significant linear relationship between the two from the previous example. Again, we don't really care about the context for this problem. We're just testing the numbers. Testing the numbers is the same in every context. So rather than confuse you guys with some context, I kind of kept the context out of this problem. If a researcher hypothesized a positive linear relationship between two variables, so let's say the researcher believes that there is a positive linear relationship, then rho would be greater than 0 for my alternate. However, if the researcher hypothesized a negative linear relationship between the two variables, then my alternate, or the researcher's alternate, would be believed to be less than 0. Okay? Correlation and causation. The nature of the linear relationship between the independent variable x and the dependent variable y when a hypothesis test indicates that a significant linear relationship exists between the variables. So we're going to be talking about correlation and causation. Again, just because two things are correlated does not mean that, it caused it, right? I mean, I can say like an example I've given before, the price of ice cream went up, mass shooting went up. There's a correlation between the two. They both went up. That means nothing. Just because the price of ice cream went up does not mean that it caused, mass shooting. A lot of media does that where they connect two, mm, have nothing to do with one another, but the correlation is strong, so they assume that they caused it. So correlation does not mean causation. When two variables are highly correlated, item 3 in the box states that there exists a possibility that the correlation is due to a third variable. If this is the case and the third variable is unknown to the researcher or not accounted for in the study, it is called a lurking variable. An attempt should be made by the researcher to identify such variables and to use methods to control their influence. So if you recall from chapter 1, we talked about, chapter 1, section 4, we talked about lurking variables or confounding variables. Sometimes there's a possibility of a third. Back to my carbs, fats example, sugar could be an effect. I mean, yes, I added the carbs, but did I account for the sugar? Did I account for, the sodium in the food that I have? So in some cases, there could be lurking variables that are affecting it. Now we do these exams, these tests, and these homework problems, and we assume that we're just looking at these two, and we're not worried about the rest. So this is more for just the information to learn that there is a third option, there is a fourth option, there are lurking variables. But for us, we just worry about two. Okay, we're just worrying about the response variable and the independent, dependent, the explanatory, and the response variable. Alright, so now we're going to talk about the regression line or the best fit line. So when we have a scatter plot and we have a bunch of different points, we want to find the line that best fits all of these lines. So it's not necessarily has to touch the points, not necessarily has to go through every point. Obviously, we cannot have a line that possibly can go through every point. However, we want to find the line that truly finds the best kind of average of every point and kind of goes through as many as possible. So the idea to find it is you want to find the observed value, so every point is considered the observed value. The line has the predicted values, and the difference between the predicted value and observed value is kind of, you want to think of it as an average, so you have an average difference throughout. So as you can see that not every difference is the same. So what we want to find is kind of an overall average, an overall line that can predict most points as accurate as possible, maybe a couple of decimals apart. And that would be our regression line. From before, if you look at the graph on the left, from before we're used to saying y equals mx plus b. So we are used to saying that m is the slope, x is the variable, plus b, which is the intercept. However, if you look in the right, in statistician notation, we don't say mx plus b, we say a plus bx. Bx, this time b is the slope and a is the y-intercept. So it is the same concept, no difference when it comes to meaning. The difference is only how it looks. So just think of it as y equals b plus mx. So you're kind of like flipping the b and the m. But in this case, b indicates slope, not m. So it could be confusing if you're so used to y equals mx plus b, but we're just changing the letters. So in this case, b is m, which is the slope, and a is the y-intercept. So kind of get used to that for this chapter. The formulas for the regression line for a, similar to when we were calculating for r, you're going to find sigma y, sigma x squared. So sigma x squared just means you take the square of every x, and then you add them up. You sum them all up, and then you add up all the y's. Same concept for b. just some different summations. You have summation of xy, you have summation of x, summation of y. The bottom one, if you look down here, it's very crucial that it's on the outside. And the difference between the outside and the inside is that for this one here, so let me just erase. For this one here, we are adding all the x squares. So x squared for the first data point plus the next data point squared plus the next data point squared. So you have x1, x2, x3 all being squared. Sorry for the bad handwriting. For the next one, this one here, when the squared is on the outside, that means I'm adding up all the x's. So x1 plus x2 dot dot dot. And then once I add them all up, I square the final result. So that's the difference between the squared on the outside, squared on the inside. Again, A, where A is the y-intercept, keep that in mind, and B is the slope of the line. And the rounding rule for the intercept and the slope, round the values of A and B to 3 decimal places. So normally you would just round to 3 decimal places. That's usually your case. So let's look at an example. Alright, so find the equation of the regression line for the data given and graph the line on the scatter plot of the data. So again, this is an example that we did in the beginning of the video. We found R. Now we're going to find the regression line. So we have the data points, we have the revenue. What we're going to do is the values needed for the equation are n equals 6 because we have sample of 6 data points. The summation of x is just adding up all the x's, adding up all the y's. Multiply x times y, so every x with its corresponding y. So every data point you multiply the two, you find the sum of all, and the sum of all x squares. And when we substitute it back into the formula, as you can see here, now try this problem out. Try this problem out. You have to get these exact numbers. If you get these numbers, then you know what you're doing, and it's the same for every problem. And you should get 0.396 and 0.106. So hence the equation of the regression line for a plus bx is y equals 0.396 plus 0.1067. To graph the line, select any 2 points for x and find the corresponding values for y. Use any x values between 0 and 10 and 60. The reason for that is because the max number is 63. The lowest number is roughly, if I remember correctly, I think it was 3. So just pick a number between 10 and 60, between the two endpoints. Any two numbers, it does not matter what they are. You plug in the values you choose. So let's say you chose 15. You plug 15 into the equation. You solve for y. That's your point. That's your xy, right? Because you solved for y. Let's say we picked 40 as well. You plug in the point, you get 4.63. You found yourself your y. So now you have 2 points, 2 new points, 40, 4.636, and 15, 1.986. And all it takes is 2 points to make a line. So you put those 2 points and you make yourself your best fit line. So if you were to graph the scatter plot, right, of the 6 values that we know, and you draw the best fit line, you'll see that that line kind of goes through an average of the differences of the observed points that we know. So you'll see that it truly does look like the best line that suits most of them. It barely touches the last point, right? It barely scratches the last point. It doesn't have to go through the points. Sometimes it might go through a bunch of points. Sometimes it may not go through any points. But the idea is it crossed all of them, and it's kind of in the, again, not the average middle, but like kind of in the middle of all of them. So find the equation of the regression line for the data given and graph the line of the scatter plot. So again, try this example out on your own. You could pause the video here, try it out. Again, make sure that your x is 1, 2, 3, 4, 4, 6, and your y is 6, 2, 7, 8, 70, 90, 93, and 103. For the answer, solution, these are the values you should have gotten. Here is once you plug them in. And here is the line. So again, because the slope is negative, the line is facing from left to right. If a problem were to ask you to predict a given point, like predict, since we don't know what 12 is, right? Predict what the value would be at 12. Then you would just plug in 12 and get your value. That's it. So the regression line is the prediction line. That is the line of prediction. So we are predicting at this point, this is the value. Now, it's not going to give us the most accurate value because our data points give us the most accurate value. But we don't know what happens at 12. We don't know what happens, for example, at 4. We don't know what happens after 15, right? We don't know any of that. So that line is the best prediction. It's the best fit line. So we plug in 16 to our formula, and that should give us the best prediction estimate to what we are looking for. Again, this line or this equation is not a perfect equation. It's an equation that kind of gives us the best idea of how the data is spread. So meaning by plugging in a point, if it'll fall on a line. It will fall on the line somewhere. Wherever it lands, that is the best prediction we can make. So this is the idea of the regression line, and this is pretty much it for chapter 10. We're just going to go over the regression line and the correlation. We're not going to go any deeper into this, just the basic concept of this.